Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome to the Deep Dive. Today, we're looking at an event that, well, it really pushes the limits of what we thought was possible. We're talking about an explosion that not only set a new cosmic speed record, but also showed us, in real time, how the universe forges some of its rarest and most precious elements.
It's an incredible story. We're drawing mainly from a paper in the Astrophysical Journal that details this one event, GRB 230307A, and it's a benchmark for two completely different fields of physics, really. You have relativity on one side and cosmic chemistry on the other.
And let's just start with the number that caught everyone's attention. I mean, this thing was measured moving at 99.999998% the speed of light.
It's almost impossible to get your head around that. The margin is so incredibly small. To accelerate actual matter that close to the ultimate speed limit, it just tells you the sheer power we're dealing with.
Right. And you, the listener, should know this wasn't some decades-long project. The paper detailing this was led by a graduate student, Sarah DeLacy, at the University of Alabama in Huntsville.
Which is amazing. And her work highlights these two monumental facts. It's the fastest jet we've ever measured, and it's also the second brightest gamma-ray burst, or GRB, seen in over 50 years of looking.
Wow. Okay, so that combination of speed and brightness is what makes it so special.
Exactly. It's an absolute outlier.
Phenomenal. So here's how we're going to break this down. First, we have to talk about that speed. How on earth do you even measure that? We'll get into something called the Lorentz factor. Then we'll look at the people and the technology behind the discovery. This wasn't an accident. It was a result of a huge coordinated effort.
A very rapid one.
And finally, the big payoff. How this record-breaking burst gave us the smoking gun for where heavy elements, we're talking gold, platinum, and one in particular, tellurium, actually come from.
The cosmic kitchen, as they call it.
The cosmic kitchen. Okay, let's start with the basics. What exactly is a gamma-ray burst? We know they're the most powerful explosions out there, but what makes GRB 230307A stand out from the rest?
Well, the first thing to remember is that a GRB isn't like a bomb going off in all directions. It's a highly focused beam of energy, a jet.
Like a cosmic laser beam?
Sort of, yeah. A jet of matter and radiation moving incredibly fast. And this one, 230307A, is what scientists call ultrarelativistic, which is just a fancy way of saying its speed is so extreme that you have to use Einstein's theory of special relativity to even begin to describe it.
And that's where that 99.99998% the speed of light figure comes from. That's not just a mind-boggling number. It implies some truly insane physics are happening at the source.
It really does. And to measure that tiny difference between the jet speed and the actual speed of light, which is about 186,000 miles per second, you need a special tool. You can't just subtract one from the other.
Okay, so what is that tool?
It's a number called the Lorentz factor, often just abbreviated as LF. It's a way of quantifying the effects of moving that fast. It tells you how much an object's energy is boosted because it's approaching the speed of light.
So it's not a direct speed measurement, more like a measurement of the relativistic effects of that speed.
Precisely. And in the context of this GRB, the Lorentz factor is what we use to measure the velocity of that fireball of ejected material. A higher Lorentz factor means you're closer to the speed of light.
And astronomers can calculate this how? I mean, they're obviously not there with a radar gun.
No, they're not. It all comes down to a phenomenon called relativistic beaming or Doppler boosting.
Ah, okay. This is why they appear so incredibly bright to us, even from billions of light years away.
That's it, exactly. When the jet is moving towards you at these speeds, all the light it's emitting gets focused into this very, very narrow cone pointed right at you. The Lorentz factor quantifies how intense that focusing effect is. It makes the light appear way brighter and shifts it to higher energies than it would otherwise.
So a higher Lorentz factor means a more focused, brighter beam.
Right. And that's a huge clue. To actually get the number, astronomers have to watch the afterglow.
The afterglow being the light produced after the initial flash as the jet material slams into all the gas and dust that's just sitting around in space.
Yes. And as that jet plows into the interstellar medium, it starts to slow down. And as it slows, that beaming effect gets weaker. The light curve, the way the brightness fades over time, changes in a very specific way that depends directly on that initial Lorentz factor.
So they're modeling the decay of the light.
They're modeling the decay, looking at the spectrum, how the energy of the light changes. They look for specific signatures in the radiation. And by comparing what they see to these really sophisticated computer models, they can work backward and figure out what the initial speed must have been.
It's like seeing the skid marks and calculating how fast the car was going before it hit the brakes.
That's a great analogy, and that's how they came up with the Lorentz factor for GRB 2303U07A.
Okay, so let's put that number in perspective.
Yeah.
What did we think was fast for a GRB before this?
Well, based on, decades of observations, a typical GRB might have a Lorentz factor of maybe a few hundred, say 300.
And 300 is already something like 99.995% the speed of light, right? Already incredibly fast.
Oh, yeah. Mind-bogglingly fast. We considered anything pushing up towards a Lorentz factor of 1,000 to be, exceptionally rare and energetic. That was sort of the upper limit of what we'd seen.
But this one wasn't 1,000.
No. This one was measured at 1,600.
Wow. 1,600. That's not just breaking the record, it's shattering it.
It completely shatters it. It's a 60% jump over the previous highest confirmed measurement. There's a great quote from Dr. Peter Veyers, one of the authors, who just says, "The Lorentz factor is the measure of speed of the jet here, and 1,600 is the highest we ever measured." It's just a plain statement of a new reality.
So that number, 1,600, means the matter in that jet was moving within just 30 parts per million of the speed of light.
Yes. For you listening, just try to imagine the physics involved there. What kind of cosmic engine can take a huge amount of matter and accelerate it so perfectly, so efficiently, that it gets that close to the absolute unbreakable speed limit of the universe?
It really forces you to ask new questions. Does this mean these explosions are even more powerful than we thought? Or is there some new mechanism at play that makes the jet acceleration super efficient?
And that's the big theoretical question this whole discovery raises. An LF of 1,600 suggests that the central engine, whatever created this jet, converted its energy into outward motion with almost perfect efficiency. There was very little waste.
So what could do that? What kind of engine are we talking about?
The leading idea is that it has to involve incredibly powerful and very specifically ordered magnetic fields.
Okay.
So when you have two neutron stars merging, which we now know is what caused this, they briefly form this single super dense object that's spinning furiously, and it has a magnetic field that's just astronomical.
Stronger than anything we can imagine.
Thousands of times stronger than even a magnetar's. And as this object spins, it winds up these magnetic field lines into a kind of twisted tower. That magnetic tower acts like a nozzle, a channel, that funnels all the energy and plasma out into two perfectly straight jets.
So it's not just a messy explosion, it's a finely tuned cosmic cannon.
A perfectly engineered cosmic syringe, really. And a Lorentz factor of 1,600 tells us that for this specific event, that magnetic structure was almost flawless. It extracted energy from the merger and shot it into space with almost no loss.
Incredible. And that perfect violent efficiency is what leads us to how it was even discovered in the first place.
It does. Which brings us to the logistics. I mean, an event this fast and this bright is over in a flash. You have to be ready. You have to be watching all the time.
And the instrument that was watching was the Fermi Gamma Ray Burst Monitor, or GBM.
Yeah.
It's on NASA's Fermi Gamma Ray Space Telescope, which has been up there since 2008, basically staring at the sky, waiting for these flashes.
It's the universe's ultimate early warning system. The GBM itself has these 14 detectors positioned all around the satellite, so it's always watching the whole sky at once. And the team that runs it is a huge international collaboration.
Right, with NASA, the Max Planck Institute in Germany, and crucially, the operations hub at the University of Alabama in Huntsville.
And that's where Sarah DeLacy, the lead author, comes into the story. Because at the exact moment this burst went off, she was on duty.
What was her role? I mean, what does that actually involve in the moment?
Her official title was the burst advocate. And it's a very high-pressure, on-call position.
So she's the first human to analyze the data.
Essentially, yes. The satellite detects a burst of gamma rays and automatically sends down an alert. The computer does a quick, rough analysis. But it's the burst advocate who has to immediately jump on the raw data and figure out, okay, what are we really looking at here? Is this real? Is it important?
And the clock is ticking. You've got telescopes all over the world that need to be pointed at this thing right away if it's going to be studied.
In seconds, she has to figure out three things almost instantly. One, where is it? The localization, so other telescopes know where to look. 2, what kind of burst is it, the initial classification. And 3, how bright is it? And that last one is what set off all the alarm bells.
Right. She's quoted in the source material saying she knew that this was an extraordinarily bright event, perhaps the second or third brightest GRB ever. How do you know that in, a matter of moments?
It comes down to the photon count. The data packet from the satellite tells you how many gamma-ray photons hit the detectors per second. And the number for this event was just off the charts. Her training and experience told her immediately that this wasn't a run-of-the-mill burst. This was something historic.
And that quick expert decision is the linchpin for everything that followed.
Absolutely. Because she and the team could classify it as a major event so quickly, they triggered a global alert. They told everyone with a powerful telescope, you need to drop what you're doing and point it here, right now.
And that includes getting a request in for time on the biggest instruments we have, like the James Webb Space Telescope.
Exactly. Without that lightning-fast analysis from the burst advocate, the window to observe the afterglow would have closed. We would have seen the flash of gamma rays, but we would have missed the real prize, the kilonova that followed. The entire story of element creation would have been lost.
It's amazing that it all hinges on that one moment of human expertise. And this is the same team, I should point out, that also found the brightest GRB ever seen, just a little while earlier.
They're on an incredible run. It just shows that even with all our automated systems, you still need that sharp, trained scientist in the loop to connect the dots and realize you're seeing something truly revolutionary.
Okay, so let's pivot from the detection to what they found. The speed was the headline, the brightness got their attention, but the real scientific goldmine was in confirming what kind of explosion this actually was. And that brings us, as you said, to the kilonova.
Right. The kilonova is the key piece of evidence. The GRB itself, that's the initial focused beam of light. It's incredibly bright, but it's over quickly. The kilonova is something different. It's the faint, fading glow from the cloud of radioactive debris that's thrown out by the explosion itself.
So if the GRB is the muzzle flash of the cannon, the kilonova is the lingering cloud of smoke.
That's a perfect way to put it. And it's so important because a kilonova is the unique, unambiguous signature of two super-dense objects colliding, either two neutron stars or a neutron star in a black hole.
And why is its signature so unique? What's in that smoke cloud?
Heavy elements. Newly created heavy elements. This is where we get to that great analogy from Sarah DeLucy in the paper where she says these mergers act as a cosmic kitchen for heavy elements.
The cosmic kitchen. I love that.
Yeah.
Let's break down that recipe. Why is a neutron star merger the perfect place to cook up things like gold and platinum when a regular star exploding can't do it?
It all comes down to one crucial ingredient, neutrons. A ridiculous, unimaginable density of free neutrons.
Because the neutron star is basically just a giant ball of them.
Exactly. It's what's left after a star has collapsed and gravity has crushed all the atoms so tightly that the protons and electrons have merged to form neutrons. A single teaspoon of that stuff weighs billions of tons.
Okay.
So when two of those slam into each other, huge amounts of this pure neutron matter get ripped off and flung out into space.
And that cloud of ejected neutrons is where the magic happens.
That's where the alchemy happens. For a very brief moment, you have this cloud that is both incredibly hot and packed with more free neutrons than anywhere else in the universe. And in those conditions, you get something called the rapid neutron capture process, the R process.
Rapid being the key word there.
The key word. It means that existing atomic nuclei, like iron, are just bombarded with this flood of neutrons. They absorb neutrons faster, much faster than they have time to radioactively decay, so they just get heavier and heavier and heavier, climbing up the periodic table in a split second.
So it's a high-speed nuclear assembly line.
The ultimate assembly line. It's the only way we know of to produce most of the elements heavier than iron. So every gold wedding band, every platinum catalyst in a car, it was all forged in a cataclysm like this one.
That is just, it's incredible to think about. So we have this theory. The GRB goes off, we see the kilonova, and we say, aha, the R process is happening in there. But this observation went a step further, didn't it? They actually saw one of the elements being made.
They did, and this is the monumental part of the discovery. They found the specific spectral fingerprint of the heavy element tellurium.
Tellurium. Why is that one so important? We always hear about gold and platinum.
Well, gold and platinum are definitely being made in there, but they are incredibly difficult to see. Their atomic structures are so complex that they just create a sort of a messy, blended out spectrum in the kilonova's light. It's hard to pick out a clear signal.
They're spectroscopically noisy, you could say.
Very noisy. Tellurium, however, has a much cleaner, more distinct signature. It produces very clear absorption lines in the near-infrared part of the spectrum.
And which telescope is the undisputed king of near-infrared astronomy?
The James Webb Space Telescope. So the follow-up team in Europe knew exactly what to do. They pointed Webb at the fading glow of this event, looked at the near-infrared light, and there it was. Not an inference, not a guess from a model, but a clear, direct, unmistakable signature of tellurium.
That's the smoking gun.
That is the smoking gun. It's the first time we've ever directly identified a specific R-process element being created in the aftermath of a GRB.
So the whole chain of events is complete. The record-breaking speed got their attention, the rapid follow-up let them watch the aftermath, and the power of JWST let them look inside that aftermath and confirm that this cosmic kitchen was, in fact, cooking up tellurium, an element we use right here on Earth in things like solar panels.
It's a perfect connection, from the most extreme relativistic physics in the universe straight down to the chemistry that enables our technology. A truly remarkable piece of detective work.
So where does the field go from here? I mean, this discovery was so successful, it seems like it lays out a clear path forward for researchers like Sarah DeLacy.
It does, but it also creates a new puzzle. The big challenge now is that GRB 230307AA kind of breaks the old rules we use for classification.
How so?
Historically, the rule of thumb was pretty simple. If a GRB lasted for more than 2 seconds, it was a long burst, and we assumed it came from a massive star collapsing. If it was less than 2 seconds, a short burst, we assumed it was a merger of two compact objects.
Okay, that seems straightforward enough.
But this one, 230307A, was a long burst. It lasted for quite a while. Yet the kilonova proved, without any doubt, that its source was a merger.
So it was a long burst from a merger event. It breaks the mold.
It completely breaks a mold, and this is where the cutting-edge research is now. The biggest goal, and what DeLacy is working on, is finding more of these weird, long-duration merger events.
To see if this was a one-off freak event or a whole new class of explosion we didn't know about.
Exactly. If we can find more, it helps us understand the different ways neutron star mergers can play out. Maybe sometimes they collapse into a black hole instantly, creating a short burst, but maybe other times, like this one, they form a temporary hypermassive neutron star that survives for a few extra seconds, pumping out a longer-lasting jet.
But the big bottleneck is still there, isn't it?
Yeah.
To be sure it's a merger, you have to catch that kilonova, which means you need that massive, time-sensitive follow-up campaign with telescopes like Webb.
It is the bottleneck. It's expensive, and you have to be incredibly fast. We got lucky with 230307A because it was so bright we knew it was special. But what about a fainter one? We can't point Webb at every single long GRB just on a hunch.
So we need a way to know it's a merger before the kilonova even appears.
That's the holy grail, and that's DeLacy's specific research goal. She's trying to find a subtle signature, a hidden clue in the prompt emission, the initial flash of gamma rays itself that screams merger.
A kind of secret handshake in the light curve? What are they looking for?
They're digging through the data, looking for tiny differences between the jets from mergers and the jets from collapsing stars. Maybe the jet from a merger has a slightly different temperature or a slightly different energy spectrum because it's blasting out into a cleaner environment.
Whereas the jet from a collapsing star has to punch its way out of the star's outer layers first.
Right, and that might leave a mark on the gamma ray signal. They're looking for subtle wiggles in the light curve or changes in the spectral properties. It's a huge data analysis challenge, but if they can crack it.
If they can crack it, they can know a long GRB is from a merger in milliseconds, not days.
And that changes everything. It means we can trigger follow-up observations instantly and systematically. We stop relying on luck and brightness, and we start being able to study every single one of these element factories that goes off, no matter how faint.
It moves the whole field from being reactive to being predictive, making sure we never miss another one of these cosmic kitchens in action.
That's the goal.
What a fantastic story. So, to sum this all up, we dove into GRB 230307A, an event that set a stunning new speed record. with a jet moving at 99.99998% the speed of light, which corresponds to a Lorentz factor of 1600.
A number that really blew past all previous records. We saw how a rapid response team, with a graduate student at the center of the action, caught this fleeting event using the Fermi GBM. And that speed allowed for the crucial follow-up with the James Webb Space Telescope.
Which, in turn, led to the grand finale. The first ever direct confirmation of a specific heavy element, tellurium, being forged in the kilonova of a neutron star merger.
Proving that these violent cosmic collisions are indeed the factories that create the heavy elements we find all around us.
The future now lies in trying to find a way to identify these merger events from their initial flash alone, to make these discoveries routine rather than revolutionary.
And that leaves us with, I think, a really interesting final thought for you to take away. We now know for sure that this process works, but our ability to confirm it depended on this event being an extreme outlier, one of the brightest ever seen. So the question is this. If the average GRB is much fainter, much harder to follow up on, how many of these art process events have we already missed? How much of the universe's gold, platinum, and tellurium has been created in explosions that we saw but just couldn't classify in time? It makes you wonder what cosmic history is still hiding in plain sight.